When it comes to the synthesis of an amide, there's three functional groups that we've talked about that would allow you to make an amide. Do you know what they are? Pause the video, go through your notes, and come up with 3 ways that you could make the amide shown here. So, if you've thought about the ways that we know how to make amides, the first way that we could make this amide is from an acid chloride functional group. So we could take an acid chloride, like this one, and we could treat this acid chloride with an amine, so this amine. And remember that we either need 2 equivalents of this amine in the reaction or triethylamine in order to act as the base. So we could add triethylamine into that reaction, and that would give us one possible synthesis. The other way that we could make this amine that we already know is to use an anhydride, like this one here. And if I treat this anhydride with an amine, again, either 2 equivalents of the amine or in the presence of triethylamine, so we'll use 2 equivalents this time, that will allow us to make the amide product. Finally, we also know how to make amides from esters. I could take an ester, like this one here, and I could treat this ester with an amine in order to also make the amide product. Notice that one of the reactions we didn't talk about was the reaction between a carboxylic acid and an amine. So if I took this amine and this carboxylic acid and I reacted them, I don't get this product out of the reaction. What do I get? Think about it. What we know about these 2 compounds is that my carboxylic acid is acidic. It has a pKa of about 5. I also know that amines are very good nucleophiles or very good bases. So that under the conditions of this reaction, all I get is an acid-base reaction. This nitrogen can grab that proton from my carboxylic acid, give those electrons to the oxygen, and what I get out of that reaction is a carboxylate ion and an ammonium ion. I get a salt. So that the reaction of a carboxylic acid and an amine produces a salt. Our next functional group is nitriles. And nitriles are always one of students' least favorite groups. Before we get into the reactions of nitriles, let's talk about the nomenclature. When it comes to naming a nitrile, we're going to simply add nitrile to the parent. So that if I have a nitrile like this one, when I number my chain of carbons, I have 1, 2, 3. So that means my parent name is going to be propane, and when I add nitrile to the end, I'm going to get propane nitrile. Don't forget to count the carbon of the nitrile. Remember, if I draw propane nitrile, I could also draw it like this. I don't have to show that carbon, and it means the same thing. If I have a compound like this one, when I go to name this compound, I need to identify my parent chain, and my parent chain has to contain my highest priority group, which in this case is going to be the nitrile. So that gives me 1, 2, 3, 4, 5, 6, 7, 8 carbons in my parent chain. At carbon number 7, I have a methyl. At carbon number 2, I have an ethyl. So the name of this compound is going to be 2-ethyl, 7-methyl, octane, nitrile. For the reactions of nitriles, there's 2 reactions that we're going to talk about. If I have a nitrile like this one, Remember, the name of this compound is benzonitrile. That was one of your common IUPAC accepted names when we talked about aromatic compounds. This compound can undergo a hydrolysis under both acidic and basic conditions. Under acidic conditions, we're going to treat the nitrile with an acid like HCl. We need water and heat, and the product that we get out of that reaction is a carboxylic acid and an ammonium ion. If I treat that same nitrile under basic conditions, I can treat it with KOH, water, and heat. And the product that I get out of this reaction is going to be my carboxylate ion plus my neutral amine. So once again, we really have to watch our pH in this reaction. Our products are going to be a carboxylic acid and an amine, but the pH is going to dictate exactly the form that that carboxylic acid and the amine will take. Under acidic conditions, my carboxylic acid and my amine will both be protonated. My carboxylic acid will be neutral. My amine will be an ammonium ion with a positive charge. Under basic conditions, my carboxylic acid will be deprotonated as the carboxylate ion and carry that negative charge, and my amine will be present in its neutral state. So under acidic conditions, the carboxylic acid is neutral, the amine is protonated. Under basic conditions, the amine is neutral and the carboxylic acid is deprotonated. So always watch your pH in these reactions. As we begin to understand nitrile chemistry, I want to make sure you understand the resonance that we have with the nitrile. A nitrile is considered a carboxylic acid derivative, and this carbon-nitrogen bond is polar. Nitrogen is more electronegative, so the nitrogen can pull the electrons in that bond towards itself, just like the oxygen can in a carbonyl. When that happens, that gives me a resonance structure that looks like this, where my nitrogen has 2 lone pairs, my carbon is now electron deficient. So that a resonance structure tells me, like this one, that my nitrogen has a fair amount of electron density, and my carbon does not have that electron density. So my carbon is a good electrophile, like I expect based on the rest of my mechanisms. So what I want you to do is I want you to pause this video, and I want you to think about these mechanisms. Think really hard, think really carefully. This carbon of my nitrile is this carbon of my carbonyl. So you need to think about how you're going to break 3 carbon-nitrogen bonds, and you're going to make 3 carbon-oxygen bonds during the course of this mechanism. This product forms under acidic conditions, so we have a lot of protons. When we have a lot of protons around under acidic conditions, things will protonate. Neutral molecules will leave our tetrahedral intermediate. Whereas in this mechanism here, we have basic conditions. Under basic conditions, there's no protons. Things that will leave our tetrahedral intermediate are going to have a negative charge. So think through both of these mechanisms. Pause the video, think through the mechanisms, and see what you come up with. There are 3 ways to synthesize a nitrile. The first way is through diazonium salt chemistry. We learned in our unit on electrophilic aromatic substitution that if we have a diazonium salt and we treat this diazonium salt with copper 1 cyanide, we can make a nitrile. We also know that we can make a nitrile through an SN2 reaction. So that if I have an alkyl halide, like this one, and I treat it with sodium cyanide and DMSO, which are the conditions for an SN2 reaction, my cyanide group does an SN2 displacement, and I make a nitrile as my product. Notice that my starting material has 1, 2, 3, 4 carbons. My product now has 1, 2, 3, 4, 5. So that overall my nitrile has extended my carbon chain by 1 carbon. The third way to make a nitrile is the new way that we have, and this is going to be from what's called a primary amide. A primary amide is one where the nitrogen of the amide is bonded to 2 hydrogens. So this is an example of a primary amide. If I treat this primary amide with my dehydrating agent of P2O5, the product that I get out of this reaction is this one. We said before that P2O5 is a very good dehydrating agent. So as this dehydration takes place, we lose the oxygen from the carbonyl, we lose the 2 hydrogens from the amide, and this becomes our carbon-nitrogen triple bond right there. A secondary amide would have a structure like this one, and a tertiary amide would have a structure like this one.